Welcome my friends, welcome to my next lecture. Now in this lecture my plan is to talk about what is called some consequence of maximum modulus principle. Now in my last lecture I was discussed like maximum modulus theorem or maximum modulus principle. In fact I have discussed the proof of it. So today again I will just recall the statement once again, then I will see some of its consequences, and of course later you will see I will prove another beautiful theorem, another two beautiful theorems. So one of the theorem is Schwarz lemma, which will come as a consequence of maximum modulus principle, and of course you will have Morera's theorem, that is you will see later on that it is nothing but the converse of what is called Cauchy-Goussard theorem. So for today's lecture my plan is to talk about more about maximum modulus principle, and if time permits then I will go for Schwarz lemma and Morera's theorem. Okay, so as I said, so I have already discussed this theorem, maximum modulus principle or maximum modulus theorem, in my last lecture. So just to recall that what is maximum modulus theorem or maximum modulus principle is that if I have a function f which is analytic and non-constant in a given domain D, then the conclusion is that modulus of fz has no maximum value in D. That means if maximum of modulus of f exists, it has to be on the boundary, it attains on the boundary, not in the interior. In other words, there is no point z0 such that you will have this kind of inequality for all z. So if I instead of this one, if I just in one line if I say, so if I have analytic functions, suppose defined on some domain, and suppose maximum exists, maximum minima, then it attains only on the boundary and not on the interior. So if you find a point in the interior where your maximum or minimum exists, then you can conclude that you have your functions f is a constant functions. That means you do not have any other function except the constant functions which attains its maximum and minimum in the interior. That means if I have an analytic non-constant analytic functions on a domain D, and if maximum minima exists, then it always attains on the boundary and not on the interior. So that's the statement of maximum modulus theorem, or that is called maximum modulus principle. Okay, so I am not going to discuss the proof. Proof I have discussed explicitly in my last lecture. So now let me just see the so you just one point you should kind of aware of that at the very end I have used to conclude the proof of maximum modulus theorem or principle, the identity theorem. That means if you remember how I proceed for the proof of maximum modulus principle, so I started with a negation. So suppose there exists a point z0 in D where your f of z, modulus of f of z is dominated by modulus of f of z0, and this is true for all z in D. If these things happen, then by some argument or conclusions using Cauchy's integral formula and so on and so forth, I have concluded that you can have a ball or open disk, say ball of center z0 with some radius r, where my function small f becomes constant. And then I say that from if I have a domain D where my function is analytic, with the fact that there is a non-empty open set here, actually ball of center z0 radius r, where if my function is constant there, then my function is constant on the full domain. So there you can either prove it by Cauchy's integral formula, just as I said, you will have, suppose this is your domain. So in this ball of center z0 radius r, so this is r and this is the point z0. If it is constant, then you can just cover this domain by this kind of balls, and if this is constant here, you can prove that this is constant here, and so on and so forth. So you'll cover everything, so therefore your functions is constant on the full domain. Or you can apply what is called identity theorem. But right now I have not discussed what is identity theorem. Later on when I will talk about power series, there we will have the statement of identity theorem. Then that time I maybe kind of conclude that, look, if your functions f is analytic on a domain D, and if there is a non-empty open subset where my function is constant, then it's actually constant on the full domain. So therefore this is the theorem. For the time being I assumed it and proved the maximum modulus principle, but when I will talk about the statement of identity theorem and proof of identity theorem, there you will see this is the kind of, or maybe I'll just recall and justify my argument once again to conclude what is called maximum modulus theorem, proof of maximum modulus theorem. Okay, so now maximum modulus theorem, it is done. So now another version of maximum modulus theorem. What is that? So earlier one what? So if I look at the statement, so this is what? So this is the statement. Like if a function f is analytic and non-constant in a given domain D, then my modulus of f of z has no maximum value in D, or there is no point z naught, such that this should be true, right? But this is I'm saying that this is my maximum modulus theorem or maximum modulus principle. Then I am saying a stronger version. What is that? A stronger version of maximum modulus theorem. Look, what is the statement says? Says that suppose you have a function f which is continuous in a closed bounded region S. Suppose your region S is closed and bounded. Closed and bounded means it is compact. And suppose your function f is analytic and non-constant in the interior of your domain S, then the maximum value of modulus of f in S, which is always rich, occurs somewhere on the boundary and never in the interior. Now why I am saying it is a strong version? Because if you compare the two statements, in the earlier statement I am saying that there cannot have a point z naught in the interior such that modulus of f of z is less or equal to modulus of f of z naught for all z. In that theorem I am not saying whether maxima minima exist or not on the domain. Well, because I am starting with a domain in open connected set, and in open set I have a analytic functions, and I am saying that you cannot have a point z naught inside D such that modulus of f of z is dominated by modulus of f of z naught for all z in D. But I am not assuring with that theorem that maxima and minima exist. I cannot say that. But this is stronger version. That means I am starting with a domain or region which is closed and bounded, and I am starting with my functions continuous on this closed bounded set or region S. That means since S is the region S, it is closed and bounded, and my function is continuous, so therefore maxima minima always exist. So this theorem ensures you that yes, if I start with a region S which is closed and bounded, and if I start with a continuous functions on that set with the fact that f is analytic in the interior, let's say in the analytic and non-constant in the interior of S, then this theorem first ensures that yes, maximum and minimum of modulus of f always exist. Well, and then since it exists, it attains only on the boundary, not on the interior. So stronger version means earlier I cannot guarantee whether maxima or minima of modulus of f exist. But since I am starting with a functions f continuous on a closed bounded region S where my function is non-constant and analytic in the interior, then first conclusion is that maxima or minima of modulus of f always exist. See, that's what I have written, which is always reached. Because I have a compact set, I have a continuous function, so maxima minima always exist and it attains. And then question is where it attains? The conclusion is that maximum modulus theorem, it attains only on the boundary and not on the interior. Okay. So that's why I am saying that it is a stronger version compared to the other one. So other one I cannot always say that maxima minima exist. Here in this version I am always say that maxima minima always exist, but it attains only on the boundary of S but not on the interior. So that is another statement of maximum modulus theorem. You can have it. Okay. So that is why I am saying this is what is called a stronger version. Okay. So once I have a maximum modulus theorem, then you will have the corresponding minimum modulus theorem. What is minimum modulus theorem? That the following theorem is an immediate consequence of maximum modulus theorem and tells us about minimum modulus of a modulus. Minimum modulus means what? Maximum modulus means what? Modulus of your functions f. That means modulus of f of z I am talking about. That is why modulus, minimum modulus, maximum modulus is there. Now what is minimum modulus theorem? Same thing like maximum modulus. What is that? It says that suppose you have a function f which is continuous in a closed and bounded region, that means compact region, that means my maximum minima always exist. Suppose your f is analytic and non-constant throughout the interior of S, then you can say that, well, further, if assume that f of z is non-zero for every z in S, then of course modulus of f has a minimum value has minimum value in S, and which occurs only on the boundary and never in the interior. Now why I will have this kind of assumptions? Fz is non-vanishing or there is no zero in S, because you see if there is a point z naught where my function vanishes, then what is the minimum value of this? So of course I am talking about the maximum minimum value of, or say forget about maximum, so minimum value of modulus of f of z, but this is always positive, right? So therefore if at some point z naught is S and suppose f of z naught is 0, then I will say that at the point z naught it attains the minimum. Okay, so that is very trivial. So therefore by default we assume that yes, suppose I am assuming my function which is continuous on a closed bounded region S, which is non-constant, analytic, interior to S, with the fact that f is non-vanishing on the full set S, because if it vanishes at some point, and that is the minimum value, right? So therefore this is kind of automatic. There is nothing to conclude. So now if I have assumed that f of z is non-zero for every z in S, then modulus of f of z attains the minimum value, because I am starting with a closed bounded set and my function f is continuous. In the interior it is analytic and non-constant. Then modulus of f attains minimum value, and minimum attains only on the boundary, not on the interior. So like in the maximum modulus theorem. But the proof follows kind of as a consequence of maximum modulus theorem. Why? Because you see, so I have the extra assumption that assume that f of z is non-vanishing for all z in S, right? Now this is, as I said, it is automatic, because if at some point z naught, where f of z naught is 0, that means at that point z naught it attains its minimum. So therefore you kind of remove that triviality. So assume that f of z is non-vanishing for every z. Now once I assume that f of z is non-zero for every z, then I am dealing with the function g of z is equal to 1 by f of z. It makes sense perfectly, all right, right? Now look, what is your f? My function's f is continuous on what is called closed bounded region S. F is non-constant, analytic on the interior of S. So therefore the same conclusion I can say about the function g. Now my function g, which is continuous on a closed bounded region S, right? That is first statement. Then since f is non-constant and analytic in the interior of S, so therefore I can say that my function g, which is also analytic, because cosines of two analytic function is analytic function, which is also analytic in the interior of S and which is also non-constant. So therefore I can talk about something about g. Now you see, I'll go through what is called method of contradictions. What my point? My point is that modulus of f has a minimum value in S, of course, and it is attains only on the boundary, not on the interior. What I will do, so I will go through method of contradiction. Suppose modulus of f of z attains minimum at some point z naught, which is interior to S. That means there is a point z naught in the interior of S such that f of z, which is greater or equal to f of z naught, and this is true for all z in S. Suppose this is true. So then what will happen? If I consider this function g of z, which is 1 by f of z, just now I said, since my function's f is continuous on a closed bounded region S, which is non-constant, which is analytic in the interior of S, so therefore the corresponding function g, which is also continuous function, which is continuous on the closed bounded region S, which is analytic interior to S, and since your function's f attains its minimum at the point z naught interior to S, so therefore my function g attains the maximum at the point z naught interior to S, right? Because modulus of f attains kind of minimum, that means what will imply? So that means this will implies 1 by modulus of f of z, which is dominated by 1 by f of z naught, right? So therefore you can say that yes, g of z absolute is dominated by modulus of g of z naught, and this is true for all z in S, and z naught is a interior to S, right? So therefore come back to the function g. What is your function g? Your function g, which is continuous on a closed bounded region S, which is analytic in the interior of S, which is non-constant because f is non-constant, and with the assumption that suppose modulus of f attains minimum in the interior of S, implies that g, my function g, which attains maximum in the interior of S. Then what is your maximum modulus principle or maximum modulus theorem says? If I have a function which is continuous on a closed bounded region, which is non-constant, which is analytic, it cannot attain, right? And suppose if it attains, then it has to be constant. So therefore this will immediately implies that g is constant, and g is constant means g is equal to 1 by f. So 1 by f is constant, that means f is constant, and which is a contradiction because I am starting with a what is called non-constant interior functions. Okay, so that's the contradiction. So that's how you prove it. So how you prove it? Once again, I'm just repeating the proof. Proof is that you have to apply maximum modulus principle. So statement says that your function's f, which is continuous on a closed bounded region S, which is non-constant and analytic in the interior of S, which is non-vanishing on the all point in S, then I am saying that minimum of modulus of f cannot attain in the interior, it always attain on the boundary. So you have to just prove this theorem by method of contradictions. Assume that my function's modulus of f attains its minimum at some interior point z0, which belongs to interior of S. So that's what it is. Modulus of f attains minimum at some z0 interior to S. What does it mean? That means f of z modulus is greater or equal to modulus of f of z0, and this is true for all z in S. Suppose this is the case. Then what we will do, if I have this assumption, then you construct or define an auxiliary function which is g, which is 1 by f, and that makes sense because I have the assumption that f of z is non-zero for all z in S. Once I have the function g, then you can say that since f is continuous on a closed bounded region, so therefore my function g, which is continuous on a closed bounded region. Since f is analytic in interior to S, so therefore 1 by f, which is also analytic, or the function g is analytic interior to S. Now with the fact that modulus of f of g is greater or equal to modulus of f of z0, which implies that modulus of gz, which is lesser or equal to modulus of g of z0, and this is true for all z in S, and z0 belongs to interior of S. That means now look at the auxiliary function g, which is continuous on closed bounded region S, which is analytic in the interior to S, and there is a point z0 which is interior to S, and my function g of z has the property that g of z is lesser or equal to modulus of g of z0, and this is true for all z. That means the g has a maximum attains at the interior point. Then what is my maximum modulus principle or maximum modulus theorem? Says that since g is analytic interior to S, it is continuous on closed bounded region S, g cannot attain its maximum in the interior, it attains only maximum in the boundary. Since it attains maximum in the interior, there is no other options unless your function g is constant. So therefore by maximum modulus principle implies that g is constant, g is equal to 1 by f, so therefore f is constant, which contradicts the fact that I am starting with a function f which is non-constant throughout the interior of S. So and why this is a contradiction? Because I started with a wrong assumption, the fact that modulus of fz has a minimum value at the interior of S, which is not the case. So therefore modulus of fz has minimum attains only on the boundary and not on the interior. So this is a very simple application of what is called maximum modulus principle or maximum modulus theorem to conclude what is called minimum modulus theorem. That's why I have written apply maximum modulus theorem to the functions 1 by f, and since f of z is non-zero, so you can consider the functions auxiliary functions 1 by f and apply maximum modulus theorem to conclude your argument. Okay, so that's all about minimum modulus theorem. Now let me just see two examples which will be very nice. So for example, if I give this kind of problem to you, like how to solve. For example, find the maximum value and minimum value of modulus of f of z in S, where your functions I am giving f of z is equal to e to the power z, and what is my S? S is the collections of all those z where modulus of z is lesser or equal to r. Now you just draw a picture here. So what is that set S? S is a closed unit ball of center 0 radius r. That means, so this is my set, right? So this is capital R and this is the region, right? So mod z is lesser or equal to r. That means including the boundary, right? I am including the boundary. So therefore the set S, which is what kind of set it is? So since modulus of z is lesser or equal to r, that means it is closed unit disk, so therefore it is closed and as well as bounded, right? So therefore my set S is compact set, and what kind of functions you will have? F of z is equal to e to the power z. F of z e to the power z is an entire functions on the whole complex plane, so therefore it's actually analytic in the interior of mod z lesser or equal to r. That means in the domain mod z strictly less than r, it is analytic functions, it is continuous on the mod z lesser or equal to r. So therefore by maximum modulus principle, maxima minima exist, and since it exists, it always attain on the boundary mod z is equal to r and not on the interior. So I am saying that find the maximum value and minimum value. So that's how you have to apply maximum modulus principle or theorem to conclude that. Now look, since e to the power, so to apply maximum modulus theorem or minimum modulus theorem, you have to, before you apply the corresponding theorem, you need to check whether it satisfies all the hypotheses or not. Now look, so I am dealing with my functions f of z is equal to e to the power z, which is analytic functions. So therefore by maximum modulus theorem, maximum or modulus of f of z attains maximum value only on the boundary and not on the interior. Now if I have the domain S, what is the boundary? Boundary is mod z is equal to R, okay? And what is the maximum of f of z? You can explicitly calculate it. So maximum of or absolute of f of z, which is absolute of e to the power z. Now z is equal to x plus iui. If I calculate, so this is nothing but e to the power z, which is e to the power x plus iui, which is same as e to the power x times e to the power iui, but e to the iui is equal to 1, so therefore this is same as e to the power x. So therefore maximum of f of z, which is nothing but e to the power x. And by maximum modulus principle says that modulus of maximum of f of z attains only on the boundary mod z is equal to R. And since modulus of f of z is e to the power x, now e to the power x is an increasing functions where x running over, what is x? X running over R, right? So therefore you can say that, so this is my boundary, so this is mod z is equal to R, and this is my x and this is my y. So since mod z is equal to R, so therefore what x varies from where to where? X varies from minus R to R, right? If z is equal to x plus iui, so x varies from minus R to R, right? So this is my x is equal to R and this is x is equal to minus R, right? And what you will have? Modulus of f of z, which is e to the power x, right? Right? And since modulus of z is equal to R, so therefore you will have x is equal to R and x is equal to minus R. Well, in the interior, of course, is x is lying between minus R to R, but if I talk about the only on the boundary, you will have only 2 points, x is equal to R and x is equal to minus R, right? So if I have that one, then look, so modulus of f of z is equal to e to the power x, but e to the power x is an increasing functions, so that means it will attain the maximum only and the point x is equal to R. So therefore what is the maximum? That's what I have written. In S, the maximum value of e to the power z is attained only at the point z is equal to R, because it attains has to be boundary, na? Even if x run from minus R to R, but in the interior you cannot have any point where it attains, because if it attains, it has to be constant by maximum modulus theorem. But since f of z is equal to e to the power z, it's a non-constant functions, so therefore you cannot have any point x, say in between minus R to R open interval. You cannot say that my function's modulus of f of z attains the maximum. So you'll have at the only 2 points, minus R and capital R, which lies in the boundary, that means mod z is equal to R. And since I am talking about the maximum, so therefore you will have the point z is equal to R, so therefore the maximum value attains at this point, and this is nothing but e to the power R, okay? This is the kind of maximum. And what about the minimum? Same thing. Look, now it also satisfies all the properties of what is called minimum modulus theorem. First we have to conclude that, look, e to the power z is non-zero for all z in S. We already proved it. E to the power z is non-zero for all z in the complex plane, in particular all z in S. E to the power z is analytic. So therefore you can apply what is called minimum modulus theorem, because your function f of z is e to the power z, which is continuous on a closed bounded region S. Done. Then my function's f is analytic in the interior to S, which is nothing but analytic mod z is strictly less than R. On top of that, to apply minimum modulus principle, you need the extra fact that f of z should be non-zero for all z in S, and that is true because your function is e to the power z. So therefore it satisfies all the hypotheses of minimum modulus theorem. So therefore by minimum modulus theorem, minimum value of modulus of e to the power z attains only on the boundary. But what is absolute of e to the power z? Again, by calculation, this is exactly equal to e to the power x. That means I have to check the functions e to the power x, where x runs from minus R to R if it in the closed unit disc mod z less or equal to R, but it attains only on the boundary. That means you will have two possibilities, x is equal to R and x is equal to minus R. So if my function e to the power x is attains the minimum wherever x belongs, then the corresponding modulus of f of z attains the minimum. But since exponential function is an increasing function, so therefore this function attains minimum at z is equal to minus R or x is equal to minus R. That means what is the maximum value? E to the minimum value e to the power minus R. So it attains the minimum at the point z is equal to minus R, and the minimum value is e to the power minus R. It attains the maximum value at z is equal to R, and what is the maximum value? E to the power R. So that's what it is. That's what I have written. In S, the minimum value of e to the power z is attained at the point z is equal to minus R, and what is the value? Value is e to the power minus R. Similarly, in S, the maximum value of e to the power z is attained at the point z is equal to R, and what is the maximum value? E to the power R. Okay, so that's how you can apply your maximum modulus theorem and minimum modulus theorem to conclude. And if I give some problem that find a point where my functions attains maximum and minima. So first you have to check whether you want to apply maximum modulus theorem or minimum modulus theorem. You have to check it should satisfy all the properties of your maximum modulus theorem or minimum modulus theorem or not. Once you have that, then you can conclude that, look, now I can talk about that, yes, maxima minima exists and it attains only on the boundary. Then you identify the boundary of your given domain and find in the boundary at which point it should attain. For example, here is the boundary is mod z is equal to r, and absolute of f of z is nothing but e to the power x. So that means it depends only on the x variable, not on the y variable. And since x on the boundary it has two possibilities, r and minus r, and since I am dealing with e to the power x, it is an increasing function. So therefore this function attains maximum if x is equal to r or z is equal to r, and maximum value is e to the r, and attains minimum at z is equal to minus r or x is equal to minus r, and minimum value is e to the power minus r. So this is one of the very simple example to talk about. If I give this kind of problem in exams, and if you want to apply, you have to be very careful. To apply maximum modulus theorem or minimum modulus theorem, you need to verify all the hypotheses and then apply, then conclude something at point on the boundary it should attain and find out the point. Okay, so these are the tricks you need to know. This is one example. Another example, this is the one. So find, like if I say that find the maximum value of modulus of f of z in S. What is the region S? This is my region, and your functions f is sine z. Now you can draw a picture. So what is my region S? So x runs from 0 to pi, so therefore this is 0, this is pi, and y runs from 0 to 1, so this is 1. So that means I am talking about this region. So this is all boundary point included. That means x is greater or equal to 0, lesser or equal to pi, and y is greater or equal to 0, lesser or equal to 1. That means it is this kind of domain, including the boundary, right? Including the boundary. So first conclusion is that the set S which is closed and bounded, so therefore it is kind of compact set, not kind, it is a compact set. And what is your functions? My functions f of z is equal to sine z. Now sine z is an entire function in the whole complex plane. In particular, it is actually entered in the interior of S. What is the interior of S? So except the boundary, in the interior it is an analytic functions. It is continuous on S, so therefore I can apply maximum modulus principle. So by maximum modulus principle, since my function is continuous on a closed boundary region S and analytic in the interior to my region S, and f of z is equal to sine z, which is a non-constant analytic functions. So therefore maxima and minima exist or modulus of f, and it attains only on the boundary. It attains only on the boundary and not on the interior. And what I want, I would like to find the maximum value of f in S. So therefore you don't care about to get the point inside the your region S, because by maximum modulus principle it says that you just look on the boundary point, because there are infinitely many points in S, na? And I am saying that find the maximum value of modulus of f of z in S, right? So in S, by maximum modulus principle, first conclusion is that I don't care about the interior point. So I do care only on the boundary. So that means very less set you will have, so very less. And this point you know what are the points. And you have a functions f of z. So you have to find, so the first conclusion by maximum modulus principle is that, yes, from the full domain S, I am coming to the boundary. And in the boundary, at which point it attains maximum, there you need to you kind of somehow investigate or analyze, you should analyze your functions, what kind of functions I am giving you. Now since f of z is equal to sine z I have given, so modulus of f of z, which is modulus of sine z, then you apply trigonometric formula, because sine of z, which is same as sine of x plus iy, then sine a cosine b, then sine a cosine x sine iy, right? And then use the hyperbolic formula. This is sine x, what is called cosine iy plus sine iy. You just check it, okay? Yes. So you apply. You see, you just do the trigonometry. I'm not doing it here. Then you can conclude that your sine z modulus, which is nothing but square root of sine square x plus sine hyper. So you just do that one. I think this is cos hyperbolic y plus I times cosine x sine hyperbolic y, right? Then modulus of sine z, this is square root of sine x cosine hyperbolic y square plus cosine x sine hyperbolic y square. And then you use the formula that sine square x plus cosine square x is equal to 1, and I think cosine hyperbolic square y minus sine hyperbolic square y is equal to 1. So using that trigonometric formula, you will be able to conclude that your modulus of f of z, which is modulus of sine of z, which is nothing but square root of sine square x plus sine hyperbolic square y, where z is in C. So this kind of inequality I have already discussed when I was talking about my function sine z. This is actually unbounded functions. If you remember, in that lecture I have discussed this kind of equality. That means modulus of sine of z, which is square root of sine square x plus sine hyperbolic square y. It is easy. You just use the trigonometric formula, and this kind of formula you will be able to prove that one. Now, by maximum modulus principle, I said that maximum exists only on the boundary. Now I have to conclude that at which point. So first you have to investigate your functions which is absolute, which is nothing but of this kind of form. Now it is square root of sine square x plus sine hyperbolic square y, where x runs from 0 to y, 0 to pi, and y runs from 0 to 1. Now look, sine functions, I know sine square x, so what kind of functions? It is value, it is absolute is minus, it's taking value from -1 to 1. Since I am dealing with sine square x, so the minimum value is 0 and maximum value is 1, that I know. What about this function sine hyperbolic square? It is an increasing function. So now look, so therefore this function, if x runs from 0 to pi, what is the maximum value x? If x from 0 to pi, because the maximum value is 1, so therefore if I take x is equal to pi by 2, then sine square pi by 2 is 1. So this is the largest value, and this is an increasing function sine hyperbolic square y. So where it takes a kind of largest value, so largest value it is taking at y is equal to 1. That means this is the value sine hyperbolic square y, 1. So therefore the maximum value of this, since this is kind of sum of two positive square or square root, so therefore it's taking the value maximum wherever this is taking the maximum value, this is taking the maximum value. Now this is taking the maximum value at x is equal to pi by 2, and this is taking the maximum value because of increasing function sine hyperbolic y, it is taking the maximum value at 1. So therefore if I consider the point x comma y, or say x plus iy, which is pi by 2 plus I times 1, this is the point where my function's modulus of f of z attains the maximum, because this is the maximum sine square x taking the maximum value is 1, and this is the maximum value sine hyperbolic square 1, because sine hyperbolic y, it is an increasing function, and y running from 0 to 1, so it is taking the maximum value at y is equal to 1. So if I consider this point, at this point, now look at where is this point. This is x is equal to pi by 2 and y is equal to 1, right? So that means this is my pi by 2 and y is equal to 1. This is the point. So that there is this is the point in the boundary, because this point it is pi by 2 comma 1, right? Because this is 1 and this is pi by 2. So at this point my function's modulus of f of z attains the maximum value, and what is the maximum value? Maximum value is 1 plus sine hyperbolic square 1. This is the maximum value. That's what I have written. So apply the maximum modulus theorem, conclude that modulus of f attains maximum value in S at the point this on the boundary. So first conclusion is that it attains maximum on the boundary, and on the boundary at which point, there you have to investigate what kind of functions you are dealing with. Since I am dealing with sine functions, do some trigonometry. It says that it is nothing square root of sine square x plus sine hyperbolic square y. Now since x runs from 0 to y, so sine square is attain the value maximum 1 at the point x is equal to pi by 2, and sine hyperbolic square y, it is an increasing function. Since y runs from 0 to 1, it attains the maximum at the point 1. So if I consider the point x is equal to at z star, which is pi by 2 plus I, at that point it attains the maximum. Now pi by 2 plus I, it is a boundary point, and maximum value is square root of 1 plus sine hyperbolic square 1, and at no other point in S. So okay, so that's how you have to solve the kind of problem for this kind of example. So therefore if I give this kind of problem like find maximum and minimum of functions, and if I or if you would like to apply maximum modulus theorem or minimum modulus theorem, first you have to be careful that whether it satisfies, before applying maximum modulus theorem or minimum modulus theorem, whether it satisfies all the hypotheses or not. Once you kind of convince yourself, yes, it satisfies all the hypotheses of maximum modulus theorem or minimum modulus theorem, then you can say that yes, to look for where my function's modulus of f attains maximum or minima, I just look at the boundary of my region, and to check at which point on the boundary, there you need to investigate what kind of functions you are dealing with. Okay, so there you have to estimate modulus of f, look what expression you will have, and depending on some basic analysis, you can conclude that yes, this is the point where my function's modulus of f attain maxima or minima. So this is kind of two examples I have discussed. So maybe you can expect a couple of problems in your exams or in your assignment as well. Okay. Okay, so this is another one. So this is like maximum modulus of real part of f and imaginary part of f if f is analytic. That means till now I am talking about that if my functions f satisfies all the hypotheses of maximum modulus theorem or minimum modulus theorem, then I am saying that at when my modulus of f attains maxima or minima. Now instead of modulus of f, or if I have analytic functions, what can I say about the real part of f and imaginary part of f? That means I have a functions analytic in some domain, and suppose it satisfies all the hypotheses of say maximum modulus theorem or minimum modulus theorem, then when can I say that if I write f of the form u plus iv, then I can say that yes, look, real part of f attains maximum there and imaginary part of f maximum there. That is why I am saying maximum values of real part of f and imaginary part of f instead of modulus of f. Maximum modulus theorem and minimum modulus theorem says that maximum minima of modulus of f. Now I want to have a discussion, can I say something about the real part of f and imaginary part of f? Answer is yes, you can say that. For example, suppose your function f is analytic, so I can write my functions f u plus iv, perfectly alright, because any functions I can write it, which is non-constant, which is analytic functions in a closed and bounded set, okay. Now I want to say the maxima minima of real part of f and imaginary part of f instead of modulus of f. So modulus of f, already I have maximum modulus theorem and minimum modulus theorem, but how to deal with a real part and imaginary part of f? So this kind of trick I have already discussed in my earlier lectures. Now to talk about real part of f and imaginary part of f, you have to deal with some auxiliary functions. For example, to talk about real part of f, you consider these functions. That means you consider new function gz, which is e to the power f, right? Now if I consider e to the power f, now f is analytic given, it is a composition of two analytic functions, exponential functions and f, so therefore my function g is also analytic. And your domain S is closed and bounded, so therefore it is continuous there, it is analytic in the interior, so therefore I can apply what is called maximum modulus theorem instead of the functions modulus of f, but there I will apply maximum modulus or minimum modulus of the functions g or modulus of g. Now if I calculate the modulus of g, what is that? This is modulus of e to the power f, that means this is e to the power u plus iv. Now u and v are real valued, so what is that? This is e to the power u, that's it. So therefore now you see, so if I consider these auxiliary functions, so instead of applying maximum modulus on f, now I will apply maximum modulus on g. So now, so if f satisfies all the hypotheses of maximum modulus theorem, then my function ge also satisfies all the hypotheses of maximum modulus theorem. Then by maximum modulus theorem I can say that g attains maximum on the boundary. But what is modulus of g? It is exactly equal to e to the power u. So this is the exponential function, u is real valued. Now wherever g modulus of g attains on the boundary maximum, that means e to the power u also attains maximum, right, on the boundary, but exponential function is an increasing function. So therefore where it attains the maximum, wherever u attains the maximum, now u attains the maximum only on the boundary. So if u attains maximum on the boundary, then e to the power u attains on the boundary, therefore modulus of gz attains on the boundary. So therefore I can talk about maximum values of real part of f or imaginary part of f. It also attains maximum minima only on the boundary, not on the interior. Because if u attains maximum in the interior, say interior of S, that means e to the power u also attains maximum in the interior. That means your function g is also attains in the interior. Then by maximum modulus theorem that g is constant. Now since g is constant, that means f is constant, which is a contradiction. So therefore, like maximum modulus theorem or minimum modulus theorem, modulus of f attains maxima minima on the boundary. That means the real part of f and imaginary part of f also attain the maxima minima on the boundary. So this is to deal with real part of f, e to the power fz. Now how to deal with imaginary part of f? Same thing, you have to deal with another auxiliary function. This time I will deal with e to the power is minus I times fz. So this kind of functions I will deal with. Because what is absolute of h of z? Then you just calculate, this should be e to the power b. And then to talk about maximum of h, it is actually talk about maxima minima. So it depends on maxima minima where v attaining. And v is real valued and exponential is an increasing functions. So if v attains maximum on the boundary, then h is attains maximum on the boundary. If v attains maximum minimum in the interior, that means absolute of h, these functions also attain maxima minima in the interior, and which by maximum modulus theorem implies that if it attains, then h has to be constant, that means f has to be constant, which is a contradiction. So that's what. So consider the function g of z, which is e to the power f of z, h of z e to the power minus f of z. Observe that g and h are both analytic functions. Now look at the maximum values of g. If I calculate, this is e to the power u, this is e to the power b, are attained only on the boundary of s by maximum modulus theorem, because I am applying maximum modulus theorem on my function g and h, because it satisfies all the the hypothesis of maximum modulus theorem, so it attains on the boundary. Now look, since u and v are real valued functions and real exponential functions on R are strictly increasing functions, so therefore it follows that maximum values of u and v are attained only on the boundary and not on the interior. Because if u and v attains maximum in the interior, then I can conclude that my functions modulus of g and modulus of h attains maximum in the interior. Then by maximum modulus theorem I can conclude that my function g and h are constant. Since g constant, h constant, I can conclude that f is constant, which is a contradiction because I am starting with a non-constant. So therefore I can always say that u and v has to attain the maximum only on the boundary and not on the interior. That is what I am saying. So to talk about maximum values of real part of f, that means u, or imaginary part of f, that means b, if f is analytic, like the maximum modulus theorem for modulus of f, I can also conclude that real part of f and imaginary part of f, they also attain maximum on the boundary and not on the interior. So therefore it follows that maximum value of u and v attained only on the boundary and not on the interior. Again follows very nicely by applying, or you can have the justifications using maximum modulus theorem or minimum modulus theorem. Instead of dealing with the functions f, you have to deal with the auxiliary functions. So that's it. Okay, so I think I'm done. So this is like very brief about what is called maximum modulus theorem, minimum modulus theorem, proof of maximum modulus theorem and minimum modulus theorem, couple of consequences or couple of examples I have discussed. So now I will move my discussion in my next lecture to Schwarz lemma. You will see as a nice applications of maximum modulus theorem, I will be able to prove Schwarz lemma, and then later I will talk about what is called Morera's theorem. I think I should stop here. In my next lecture I will talk about another nice consequence of maximum modulus theorem, that is called Schwarz lemma. This is another beautiful theorem. So I think I should stop here. In my next lecture I should start with the discussion of what is called Schwarz lemma. Thank you.